State what it means by the Doppler effect. So this problem is testing about the definition of the Doppler effect. So the Doppler effect refers to the concept of frequency change. Frequency change when there is a relative motion. When there's a relative motion between the observer and the source. So for paper 2 question, the first part of a paper 2 question is frequently testing about basic definition about technical terms, such as just resolved, diffraction, or Doppler effect. All those terms are being frequently tested for topic 9 wave phenomena. So make sure that you're familiar with all those concepts. A place performs simple harmonic oscillations with a frequency of 39 Hz and an amplitude of 0.8 centimeter. Show that the maximum speed of the oscillating plate is about 20 meters per second. So we know that speed of a oscillation at any moment is equal to angular frequency multiplied by the square root of maximum amplitude minus the position or the distance from the object's equilibrium position. So I'm gonna represent this using x sub 0 square because I don't want to confuse about the symbol a here. Because we want to calculate the maximum speed, we want here to be as large as possible. So it's gonna be equal to angular frequency multiplied by amplitude, because we want here to be as large as possible. So x sub 0 is gonna be equal to 0, and the square root of a square of amplitude square is just equal to amplitude. So substituting number in this equation into this equation, the angular frequency is equal to 39, and the amplitude is equal to 8.0 centimeter. Convert this to meter, we need to multiply by 10 to the negative to the power of negative 2. So let me erase the unit here. So multiply by 8.0, convert centimeter to meter. We multiply 10 with the power of negative 2, and this is equal to 19.6 meter per second, which is approximately equal to 20 meter per second. The sound of frequency 2400 Hz is emitted from a stationary source towards the oscillating plate in part B. So here is the plate. The speed of the sound is equal to 340 meter per second. Determine the maximum frequency of the sound that is received back at the source after reflection at the plate. So this question is very typical. It's very classical in non-IB physics, but all physics curriculum when studying about the Doppler effect. So initially, this is the sound is emitted from the stationary source to the oscillating plate. So here the plate will be the observer we talk about in the Doppler effect, and it's moving, right? So this is gonna be a moving observer. Because we want the frequency to be maximum, we know that the observer must be approaching the source. Right. So the frequency when the sound is emitted towards the oscillating plate, which is before the reflection, is equal to this. So the observed frequency is equal to the natural frequency of the sound, which is 2400 in this case, multiplied by velocity of the sun, which is 340 meters per second, plus velocity of the moving observer, so moving observer, divided by the velocity of the speed. So this is the maximum frequency we observe when the source is emitted to the oscillating plate, right? And this is equal to 2,400 multiplied by so velocity of the sun is equal to 340 plus velocity of the observer, which is a plate, is equal to, so we calculate in part B is equal to 90.6 divided by velocity of the wave, so 340. So this is the maximum frequency when the sun is emitted from the stationary source. But the question is asking the frequency of the sun that is received back from the source after being reflected at the plate. So now the sun is being reflected. Right. So being reflected, and we are asking to solve for the maximum frequency. So we know that, let's say the frequency here is f sub 2 is equal to the natural frequency, and because this is being reflected, the natural frequency is equal to f sub 0 here. Right. Plus, so here in this case, when it is reflected, here is gonna be the moving source, whereas here is gonna be a stationary observer. So make sure you understand the switch here. So stationary observer. How do you spell observer? O-B-S-E-R-V-E-R. And same thing, we want the value here to be as large as possible. So it's going to be equal to velocity of the wave divided by velocity of the wave minus velocity of the source. And this is gonna be equal to this equation here. So I'm just gonna copy it. Right, so this is the equation we have, and the v here cancels off. So it's gonna be equal to 2,400 multiplied by 340 plus 0.6 divided by 340 minus, here is velocity of the source, which is 90.6. And this is gonna be equal to 2,700 hertz. Right. So the hard part here is to understand before reflection, the sun is emitted from a stationary source, and the oscillating plate is a moving observer. So it's a case where a moving observer is approaching a source. And after the reflection, the sun is moving. So it becomes a case where a moving source is approaching a stationary observer. And when approaching something, we want the frequency to be as large as possible. So let me actually write this down just for a quick recap. So there are two cases. The first one is the moving observer. So actually, let's do moving sun or moving source. Right, so the first case is the moving source. And when the moving source is approaching the observer, the observed frequency is going to be larger than the natural frequency of the sun. And this observed frequency is equal to the natural frequency multiplied by velocity of the sun. So let me write this down. Velocity of the sun divided by, so here velocity of the sun minus velocity of the source. And it does make sense because the negative sign allows the frequency to be larger. And when the source is moving away from the observer, the observed frequency is smaller than the natural frequency. And the observed frequency is equal to the natural frequency multiplied by velocity of the sun divided by velocity of the sun plus velocity of the source. Right. So this is the first case. And the second case is a moving observer. So same thing, approaching. So when the observer is approaching the sun, the source, the observed frequency is larger than the natural frequency. And the observed frequency is equal to the natural frequency multiplied by the velocity of the sun plus velocity of the moving observer divided by the velocity of the sun. Sorry for my horrible handwriting. And when the observer moves away from the source, the observed frequency is less than the natural frequency. And the observed frequency is equal to the natural frequency multiplied by the velocity of the sun minus velocity of the observer divided by the velocity of the sun. Right? So here are some important equations. Try to understand them instead of memorizing them. The graph shows the variation with the fraction angle of the intensity of light after it has passed through 4 parallel slits. The number of slits is increased, but their separation and width stay the same. All slits are illuminated. State what will happen to the angular position of the primary maximum. So we know that slit separation multiplied by sine theta, where theta is the angular position, is equal to m multiplied by lambda. And because the slit separation is not changed, and wavelength is also not changed, right? Because we know only the number of slits is increased. Then the angular position will remain unchanged. So what happened to the width of the primary maximum? So we know the number of slits increase, which means that more light passes through. And when this occurs, the width of the primary maximum will decreases. So this one is asking about your understanding about the impact of slit width and slit separation on the graph. So when intensity increases, the maxima, let's say initially something like this, right? It will become more, the maximum here will be sharper, will be something like this as the intensity increases. So the width here decreases. the intensity of the secondary maximum. So when intensity increases, the intensity of the secondary maximum decreases, and the secondary maximum usually occur for destructive interference.